July 1944. The rugged hills of central Italy. British tank crews watched in astonishment as a massive German Panther tank sat immobilized on the roadside, its crew frantically working on an overheated engine. This wasn't supposed to happen. The Panther was Germany's answer to Soviet armor superiority, a technological marvel that combined thick sloped armor with a devastating 75mm gun. Allied intelligence had warned that Panthers could destroy 5 Sherman tanks before being knocked out themselves. British commanders feared them. American tankers dreaded facing them. Soviet reports described them as nearly invincible from the front. Yet here sat one of Germany's most feared weapons, disabled not by enemy fire but by mechanical failure. The crew hadn't abandoned the tank because of combat damage. They'd stopped because the Panther simply broke down. Within hours, British engineers would begin discovering a truth that would fundamentally alter Allied understanding of German armoured warfare. The Panther had first appeared at the Battle of Kursk in July 1943, where it immediately established a fearsome reputation. German propaganda celebrated it as the ultimate tank, superior to anything the Allies fielded. The numbers seemed to support the claims. The Panther's 75mm Quarka 42 gun could penetrate any Allied tank at ranges exceeding 2,000 meters. Its frontal armor, 80mm thick and sloped at 55 degrees, was effectively immune to most Allied anti-tank weapons. The interleaved road wheel suspension provided a smooth ride even over rough terrain. The powerful Maybach HL 230 engine delivered 700 horsepower, giving the 45-ton tank excellent mobility. On paper, the Panther represented everything a modern tank should be. In reality, it was a mechanical disaster waiting to unfold. The British tank that encountered the disabled Panther belonged to units operating in central Italy during the summer offensive. The Churchill approached cautiously, expecting resistance, but found only German crewmen desperately trying to restart their overheating engine. A brief firefight ensued, and the surviving crew members fled, abandoning their sophisticated weapon to the enemy. British recovery teams arrived within hours, eager to examine Germany's secret weapon up close. What they discovered would prove more valuable than capturing 100 Panthers in combat. The tank's engine compartment told a story of fundamental design problems. Oil had leaked from multiple gaskets, creating puddles beneath the hull. Fuel lines showed evidence of seepage, filling the sealed engine bay with flammable vapors. The cooling system had failed to maintain safe operating temperatures, despite the engine running well below maximum power. Burn marks on various components suggested the Panther had experienced at least one engine fire that crews had managed to extinguish. British mechanics spent days getting the captured Panther operational enough for transport. Even after repairs, the tank demonstrated disturbing characteristics. Steering was extremely stiff, requiring significant physical effort from the driver. The 2 highest gears couldn't be engaged even on flat terrain, suggesting transmission problems. After just 3 kilometers of driving, the driver's compartment began filling with the smell of burning oil, indicating continued leakage problems that posed serious fire risks. Senior officers watched nervously as the Panther coughed, smoked, and struggled through basic maneuvers. Then it was sent to Britain for comprehensive testing. The British weren't the only ones capturing Panthers. American forces in Italy had been conducting field penetration trials on abandoned German armor since early summer 1944. 2 Panthers were located near Anzio, both abandoned intact. Neither had been destroyed by Allied weapons. Both had been immobilized by mechanical breakdowns that made recovery impossible under combat conditions. American technical intelligence officers immediately organized systematic testing. They fired captured German anti-tank weapons at the Panthers to evaluate armor quality while documenting every mechanical characteristic. The results shocked American engineers who had assumed German metallurgy was superior to Allied capabilities. When struck with armor-piercing projectiles, the frontal plates cracked instead of deflecting shots cleanly. After several impacts in the same area, thick armor sections literally fell apart, separating from the main structure along weld lines and stress fractures. This wasn't how properly hardened armor steel should behave. Chemical analysis revealed disturbing truths. The Panthers were using substitute alloys because Germany could no longer obtain proper materials. The armor had been surface-hardened, making it brittle throughout rather than tough and resilient as proper armor steel required. American metallurgists concluded that German industry was no longer capable of producing armor to pre-war specifications. Strategic bombing, resource shortages, and territorial losses had degraded German metallurgical capabilities so severely that even their newest tanks used substandard materials. Meanwhile, the captured Panther arrived at Britain's fighting vehicle proving establishment in late summer 1944, displaying chassis number 213101, manufactured by Maschinenfabrik Niedersachsen Hanover in June 1943. This was an early production Ausführung D model, one of the first major production variants. British engineers approached evaluation with professional curiosity mixed with genuine concern. They'd seen combat reports describing Panthers destroying British tanks with impunity. They needed to understand this weapon that had dominated battlefields from Kursk to Normandy. The testing protocol called for comparative trials against British and American tanks, including the Cromwell, Sherman, and Churchill. Engineers mounted instruments to measure engine temperature, transmission heat, suspension performance, and fuel consumption. They prepared detailed checklists and assembled spare parts from other captured vehicles. Then they started the Maybach engine. The engine roared impressively. 700 horsepower of German engineering. The Panther moved forward smoothly, its sophisticated suspension providing the comfortable ride that impressed even critical observers. For the first few hours, performance seemed reasonable. Acceleration was good, transmission shifted smoothly, handling appeared responsive despite the vehicle's considerable weight. Then, after approximately 30 kilometers of mixed driving, the engine began misfiring. Initially subtle, the problem became progressively worse. Engine temperatures climbed dangerously above safe ranges. Power output dropped noticeably. After completing just 2 laps of the cross-country course, with temperature readings exceeding all specifications, testing had to be abandoned. The engine was simply too unreliable to continue. British mechanics spent days examining the Maybach engine, discovering problems far beyond combat damage or poor maintenance. Valve pins showed premature wear. Fan drive gears were grinding themselves apart. The cooling system couldn't maintain safe temperatures even during moderate operation. Most disturbing, the sealed engine compartment designed for deep water fording meant any fuel or oil leaks created extreme fire hazards. Engineers calculated that petroleum vapor concentration in the engine bay during operation exceeded safe limits by a factor of 3. One backfire could turn the entire rear compartment into an inferno. But engine problems paled compared to what engineers discovered about the transmission and final drive. The Panther used a sophisticated ZF-AK 7200 transmission with 7 forward gears offering theoretically excellent performance. British engineers acknowledged the transmission was well designed with good gear ratios. The problem wasn't the gearbox itself. It was what came after. The Panther's final drive assembly transmitted power from the transmission to the drive sprockets turning the tracks. This critical component was fundamentally, catastrophically flawed. Original German specifications had called for epicyclic planetary gears, similar to those in the Tiger heavy tank. Planetary gears distribute loads evenly and handle high torque reliably. But Germany faced severe shortages of specialized machine tools needed to produce internal ring gears for planetary systems. To accelerate production and use existing Panzer III and Panzer IV machinery, German engineers made a fateful compromise. They switched to simpler double-spur gears. Spur gears have inherently higher internal stress loads and impact forces compared to planetary systems. They're less forgiving of shock loading and more vulnerable to driver error. This might have worked in a 30-ton tank. The Panther weighed 45 tons, 50% heavier than the drivetrain was designed to handle. Every acceleration, every turn, every bump transmitted massive stress directly through gear teeth already operating at design limits. British engineers examining the failed final drive found gear teeth that had been literally chewed apart by stress loads. Bearing surfaces showed extreme wear patterns after minimal operation. The gear housing itself had developed stress cracks. The assembly had failed after less than 300 kilometers, much of that on smooth roads rather than combat conditions. If the final drive couldn't survive 300 kilometers of testing, how could it possibly survive combat operations? The answer came from multiple sources. German prisoners of war interrogated after capture in Normandy revealed truths that Allied intelligence had suspected but couldn't prove. German tankers knew their Panthers were mechanically fragile. They understood the final drives broke easily. They recognized that engines overheated and caught fire. German commanders had developed elaborate procedures to work around Panther limitations. Panthers were routinely transported by rail even for distances as short as 25 kilometers to preserve engine and drivetrain life. Tank drivers received special training emphasizing gentle operation, avoiding sudden acceleration, making gradual turns, and anticipating terrain to minimize shock loads. Combat commanders positioned Panzer IV reserves 1,000 meters behind Panther formations, specifically to protect the Panthers' vulnerable flanks, because Panthers couldn't maneuver quickly without risking mechanical failure. German maintenance records showed Panther battalions routinely operated at below 50% readiness. At Kursk, where Panthers debuted, 184 went into action on day 1. After just 1 week, only 38 remained operational. The rest had been lost primarily to mechanical breakdown rather than enemy action. By August 1944, Allied technical intelligence compiled comprehensive reports painting a devastating picture. A British examination of 96 Panthers captured between August 8th and 31st revealed the causes of loss. Only 11 were destroyed by armor-piercing shot, 1 by shaped charges, 1 by high explosive artillery, 2 by aircraft rockets, and 1 by aircraft cannon. 44 were deliberately destroyed by their own crews to prevent capture after mechanical failures. 30 were simply abandoned when breakdowns made recovery impossible. 6 were lost to unknown causes. The mathematics were damning. Out of 96 Panthers, only 16 had actually been destroyed by Allied weapons. 80 had been abandoned or destroyed by German crews, almost certainly due to mechanical failures. German field maintenance reports confirmed the catastrophe unfolding. Panzer Regiment 2 reported in April 1944 that only 4 out of 7 operational Panthers had managed 1,500 to 1,800 kilometers without transmission failure. That was considered successful. Panzer Regiment 1 reported in February 1944 that engine life averaged only 700 to 1,000 kilometers before requiring major overhaul. By June 1944, after the Normandy invasion began, General Heinz Guderian himself acknowledged the crisis. "The Panther is inclined to catch fire quickly," he reported. "The lifetime of the Panther's engines is much higher than the Panther's final drives. A solution to the final drive problem is immediately needed." This admission from Germany's Inspector General of Armoured Forces was remarkable. Even German High Command acknowledged that more than a year after entering production, the Panther still suffered critical reliability problems with no solution in sight. The most damning evidence emerged from French army evaluations conducted after the war. France captured substantial numbers of Panthers in late 1944 and operated them until 1949, providing years of peacetime evaluation with proper maintenance. The French report titled Le Panther, 1947 documented findings that validated every Allied concern. The truly weak spot of the Panther is its final drive, which is of too weak a design and has an average fatigue life of only 150 kilometers, the report stated explicitly. This matched what British testing had revealed, with their captured Panther's final drive failing after approximately 300 kilometers of mixed driving, about half on roads and half cross-country. The turret traverse drive was too weak to hold the turret in place on slopes exceeding 20 degrees, track and running. Gear averaged 2,000 to 3,000 kilometers between failures. The engine averaged 1,000 kilometers before requiring major overhaul, with a maximum of 1,500 kilometers under optimal conditions. These weren't findings from combat-damaged tanks or vehicles poorly maintained by retreating armies. These were peacetime evaluations by professional mechanics with proper facilities and spare parts access. The comparison to Allied tanks was stark. American Sherman tanks achieved engine lives exceeding 5,000 kilometers between major overhauls. British Cromwells travelled over 6,000 kilometers reliably. Soviet 34s, despite crude construction, had drivetrain lives double the Panthers. Allied intelligence began understanding that German tank doctrine had been shaped more by mechanical limitations than tactical preferences. Panthers operated defensively, not because defensive tactics were optimal, but because the tanks couldn't sustain mechanical stresses of offensive operations. German armour travelled by rail not for convenience, but because driving to battlefields would cause mechanical casualties before combat began. American engineers testing Panthers in late 1944 at Aberdeen Proving Ground documented problems with scientific precision. The assessment concluded that Panthers were poorly suited for rapid mobile warfare that American doctrine preferred. The tank was front-heavy, quickly wearing out inadequate final drives. It had a high silhouette, making it an easy target. The sensitive powertrain required highly trained drivers who were increasingly unavailable as Germany's manpower crisis worsened. Weak side armour made it vulnerable to flanking attacks. The tank's width and long gun barrel reduced maneuverability in villages and forests. Fuel lines made from porous material allowed gasoline fumes to escape into crew compartments, creating grave fire hazards. British post-war evaluations reached similar conclusions. Between 1945 and 1947, British occupation forces in Germany produced Panthers under controlled conditions using captured tooling and German workers. These post-war Panthers underwent extended testing, confirming every reliability problem identified earlier. One British report from 1946 attempted comprehensive performance trials on 5 Panthers, including 2 gun tanks, 2 Jag Panthers, and 1 recovery vehicle. The report's opening was remarkable in its bluntness. On commencement of the trials, it soon became apparent that, owing to the inherent unreliability of the steering mechanism and the proclivity of the engine to catch fire, it would be impractical, if not impossible, to cover the full trials program. The trials were abandoned after multiple steering failures and engine fires. The Panther had defeated evaluation attempts not through superior performance but through mechanical failure. Allied commanders learned that damaged Panthers almost never escaped. If a Panther's engine was hit, if tracks were damaged, if anything immobilized the vehicle, German crews almost always abandoned it. The tank was simply too difficult to recover and repair under field conditions. Specialized Berger Panther recovery vehicles designed specifically to retrieve disabled Panthers were themselves mechanically unreliable, often breaking down while attempting tows. By late 1944, Allied intelligence understood the full scope of German armoured problems. The Panther wasn't unique. The Tiger suffered similar mechanical issues, though its planetary final drives were more reliable than Panther spur gears. The King Tiger was even worse, with final drive failures so common that the first 5 delivered to Panzer Lehr Division broke down before combat and had to be destroyed to prevent capture. The numbers told a clear story. Germany produced approximately 6,500 Panthers between 1943 and 1945. At peak strength in September 1944, some 522 were operational on the Eastern Front out of 728 total, an operational rate of 72%. That was the high point. For most of 1944, operational rates hovered around 50%. In Normandy during summer 1944, Panther battalions routinely had 1/3 or fewer tanks actually capable of combat. Compare that to American armoured divisions maintaining operational rates above 85% throughout the European campaign. British armoured brigades kept 75 to 80% of tanks operational even during sustained combat. Soviet tank armies kept over 70% of 34s running despite crude maintenance and harsh conditions. A tank requiring major repair every 150 kilometers cannot conduct mobile warfare, cannot pursue defeated enemies, cannot exploit breakthroughs, and cannot respond rapidly to changing battlefield conditions. The Panther became essentially a mobile pillbox, effective defending prepared positions where its excellent gun and frontal armour could dominate open areas, but catastrophic when required to manoeuvre. German commanders adapted accordingly, using Panthers as long-range sniper vehicles positioned defensively. This doctrine played to strengths while minimizing weaknesses, but also meant Germany surrendered initiative, allowing Allied forces to choose when and where to attack. The psychological impact on Allied forces was profound. For months, tankers had feared Panthers, had developed elaborate tactics to avoid frontal engagements, had suffered casualties trying to flank the formidable vehicles. Discovering that the feared Panther was mechanically fragile fundamentally changed tactical thinking. American tank destroyer battalions modified tactics to emphasize mobility over armor, knowing that if they could flank Panthers, they wouldn't need heavy protection because Panthers couldn't chase them effectively. British armored units became more aggressive, accepting that casualties were inevitable but recognizing Panthers were unlikely to sustain prolonged engagements. Soviet commanders, who had always emphasized mass over sophistication, felt vindicated. Their crude but reliable 34s could be repaired in field workshops, while Panthers sat disabled, waiting for parts that might never arrive. The lessons extended beyond World War II, influencing tank design for decades. American post-war development emphasized reliability as co-equal with firepower and protection. The M46 Patton, M47, M48, and eventually M60 series all reflected doctrines shaped by studying Panther failures. Soviet designers continued their philosophy of simple, robust engineering, creating the T-54 and T-55 series, tanks that were mechanically unsophisticated but could be manufactured by thousands and maintained under field conditions. British development moved toward the Centurion, prioritizing reliability and maintainability alongside combat capability. When West Germany rearmed in the 1950s and developed Leopard tanks, German engineers specifically addressed Panther failings, using reliable powertrains with properly engineered final drives and prioritizing mechanical reliability over raw performance. The story of the Panther became part of armored warfare folklore, a cautionary tale taught to engineering students and tank designers for generations. It illustrated a fundamental truth about military equipment. Performance without reliability creates false confidence, encourages poor tactical decisions, and wastes scarce resources on vehicles that cannot fulfill intended roles. The Panther looked formidable on paper with impressive specifications. In propaganda films, it appeared unstoppable. In static displays, it intimidated observers. But in sustained combat operations, it failed its crews and crippled German armored doctrine. Allied engineers' testing captured Panthers uncovered not just mechanical flaws but fundamental failures of German military-industrial planning. The revelation explained why Germany lost the armored war despite fielding technologically advanced vehicles. Superior technology means nothing if it cannot be sustained in combat. The Panther's final drive, snapping after just 150 kilometers of operation, became a symbol of everything wrong with late-war German military production. It represented prioritizing performance over reliability, rushing designs into combat without adequate testing, using inferior materials while maintaining claims of technological superiority, and failing to understand that wars are won not by the most impressive weapons but by the most effective ones. By war's end, the Panther's reputation had transformed completely. What began as Germany's Deo answer to Allied armor superiority ended as a testament to the principle that reliability matters more than raw capability. German engineering had created a vehicle with outstanding characteristics on paper, but those characteristics meant nothing when the tank couldn't reach the battlefield or had to be abandoned after minimal use. The Allied discovery of Panther mechanical fragility represented one of the war's most significant intelligence coups, achieved not through espionage or code-breaking, but through simple systematic testing of captured equipment. The knowledge that Panthers were mechanically vulnerable despite fearsome reputations allowed Allied forces to engage them more aggressively, knowing that time and movement worked against German armor. The lesson resonated through subsequent decades of military vehicle development. Every major army learned that mechanical reliability must be engineered into vehicles from the beginning, not added as an afterthought. Field. Maintenance capabilities must be considered during design phases. Drive trains must be matched to vehicle weights with adequate safety margins. Testing must be comprehensive and honest, not rushed to meet production schedules. These principles, learned at considerable cost during World War II, became foundational to modern military vehicle development, ensuring that the Panthers' failures taught lessons that prevented similar catastrophes in future conflicts.